Okay, so as promised, we're going to do a review session today to go over what we've talked about and also do different types of problem so you know how to approach every problem that you have. Ready to do it? Okay, here's problem number 1. And do me a favor, for every problem that I put up, pause me, I won't take it personal, do the problem, unpause me, and then see how I got the answer, and then check it with your answer. So the first one, it says calculate the pH of 0.200 molar sulfuric acid. Now, okay, we're talking about figuring out pH. You know how to do that. So we're looking for hydronium concentration or hydroxide concentration. Now, the acid that they give us is sulfuric acid. The key is sulfuric acid is a strong acid. So you need to decide that right away, that what I've given you is a strong acid, a strong base, is it weak acid or is it weak base? I go, okay, so I have a strong acid. Now, that makes it a little bit easier. So if I have sulfuric acid, which is a strong acid, I know strong acid is going to have 100% dissociation, so it's going to break up into 2H plus and sulfate. So far so good. There's no equilibrium. I don't need an ice table because it's a strong acid. Now, in this problem, they tell you have 2.200 molar sulfuric acid, and you know that every single sulfuric acid is going to break up into H plus and sulfate. Now, when one sulfuric acid breaks up, you end up having 2 H plus. It's a 1-to-2 ratio. So if 0.200 molar sulfuric acid break up, how much H plus you end up having? 0.400 molar, right? Because for every one sulfuric acid, you have 2 H plus. So if one breaks up, you have 2 H plus. If 2 breaks up, you have 4 H plus, right? Okay, so now I have H plus concentration, which is what I really need, because pH is minus log of hydronium or H plus concentration. As we talked about, you can use it interchangeably. Sometimes I say H plus, sometimes hydronium, but you know in your head that hydronium is a fancier way, better way than H plus. So minus log of 0.400 molar. Yeah, you guys are following me so far? Okay. Now, what answer did you get? Yeah, we get 0.398 would be my pH. It's pretty acidic, huh? And that's what I expected. It's a strong acid. So I expected a pretty acidic pH, pretty low pH. So far, so good. And one more time, I know you know this. Remember, this is 3 sig fig, right? Now, when you do log, you have to count after the decimal place to match the sig fig. And this one matches the sig fig. Yeah? Okay. So that's one type of problem you can have. If I give you a strong acid or a strong base, it's easy because it's 100% dissociation. So all you have to do, you have hydronium or hydroxide concentration, and you can figure out the pH or pOH. Ready for next one? Here's the next problem. Calculate the pH of a solution that is 0.23 molar in BOH. Kb for BOH is 4.5 times 10 to the minus 4. Well, I give you the Kb. So what that means is BOH is what? BOH is a weak base. I give you a Kb, so now what I have a weak base. Every time you have a weak base or you have a weak acid, what do you have to do? You have to do equilibrium. You have to do equilibrium, okay? So every time you have a weak acid or you have a weak base, you have to write an equilibrium. Don't forget that. Every time you have a weak acid or you have a weak base, you have to do equilibrium. So far, so good? Okay, so I'm going to write the equilibrium, and after I write the equilibrium, I have to do an ice table. Yes, ice table is back. So weak acid or base, equilibrium, and then you have to do an ice table, which is initial change and equilibrium. Okay, so far, so good. What is the initial concentration? The initial concentration is 0.23 molar, and these are 0, 0. Over time, this has to go away, and some of the product has to form. So 0.23 minus X, X, and X. So far, so good? Okay. Now again, equilibrium, ice table, and equilibrium constant, which is Kb. Equilibrium constant in this case is 4.5 times 10 to the minus 4. And equilibrium constant is product over reactant. So it will be x squared over 0.23 minus x. Nothing fancy at all. Product over reactant. We're good? Okay. Now what do we have to do? You have to figure out what x is. Okay. What did you get for x? Okay, so you probably assume that this x is 0, and you can do that because again Kb is a small number, and whatever this number is going to be so tiny compared to 0.23. It'll be so tiny compared to 0.23 that we can ignore it. Okay, so now in that case, if I do that, then what are you going to get for x? What I got for x is 0.010 molar. That's what I got for x. So far so good. Okay. Now, here's the thing. What is x? How is this going to help me out? What x represent here? X is representing hydroxide concentration. X is representing hydroxide concentration. So that's great. X is a hydroxide concentration. I can use that to figure out pOH, and then after that to figure out pH. Okay? So then I'm going to come here. I want to say, all right, so I know pOH is minus log of hydroxide concentration, and it will be minus log of 0.010 molar. So what I end up getting is 1.99 is going to be the pOH. Okay, now I know that pH plus pOH is equal to 14. As long as you figure out one of them, you can easily figure out the other one. So then I'm going to do 14 minus 1.99, and what I end up getting is 12.01 is going to be the pH. Is that what you expected? Yeah, make sure you conceptually kind of check your board. You go, okay, this is a weak base, but it's a base, so I expect the pH to be basic, right? If you end up getting an acidic pH, you probably messed up somewhere along the way. Yeah? Okay. So far, so good. So, again, I can give you a problem that have a strong acid or base, no equilibrium, just 100%. I can give you a problem that has a weak base or weak acid, then you have to do equilibrium, you have to do ice table, you have to set it up to the equilibrium constant to figure it out. Now, next one. Calculate the pH of a 0.040 molar solution of KF. What do I give you? I don't give you a strong acid or a strong base. I don't give you weak acid or weak base. What do I give you? I give you a salt. So I give you conjugate. Yeah? So I've given you a salt here. I want to give you a conjugate. So let's analyze this conjugate. So KF. Remember, the first one usually comes from the base. The second one comes from the acid. So K comes from KOH, okay? And H comes from HF, hydrofluoric acid. Now, KOH is a strong base. Conjugate of a strong base is neutral. You remember that from a couple lectures ago. We went over that a lot. If you have a strong base or acid, the conjugate would be neutral. Now here, HF is a weak acid, right? Now if you have a weak acid, the conjugate is going to be basic, right? The conjugate is going to be basic. Again, one more time. What I have is a salt. I have a salt, that means I have some sort of conjugate. So the first conjugate usually comes from a base, the second one comes from the acid. So if we have K, that probably came from KOH. And then if I have F, that probably comes from HF. KOH is a strong acid, a strong base. If you have a strong acid or base, the conjugate would be neutral. Now, if you have a weak acid, the conjugate would be conjugate base. If you had a weak base, the conjugate would be conjugate acid. So far, so good. Okay. So I have a neutral and I have a base. What do you expect the solution to be? You probably expect the solution is going to be basic. Now we're going to do the math also, but this is what we are expecting. Okay. So K is neutral, it's not going to do anything. F minus is what we are after. That is going to be my conjugate base, right? That is going to be my conjugate base. So I had KF, and KF would break up completely in water into K plus and F minus. And F minus is my conjugate base, and that's the one that I'm interested in. And remember what I said before. I said conjugate base is going to act just like a base. Even though it's a conjugate base, it doesn't matter. It's still going to act pretty much like a base. Okay? So, it's going to act like a base. What am I going to do? I have a conjugate base. I'm going to write a hydrolysis. I have a conjugate base. I'm going to write a hydrolysis, equilibrium constant. Now, don't forget. So this is a conjugate base. We keep saying that means it's going to act like a base. So if this is a base, that means the water is going to act like an acid. The base gets a hydrogen. The acid loses a hydrogen. Nothing we haven't seen before. So HF plus OH minus. So far so good. Okay. It's a conjugate base. It's going to act like a base, act like a weak base. That means we're going to have an equilibrium. And yes, the ice table is back. So far, so good. Okay. Now, what I had 0.04 molar potassium fluoride. When it has 100% dissociation in water, you're going to have K plus and F minus because every single one is going to break up. How much F minus do you end up with? 0.040 molar. Okay. 0.040 molar is what you end up ending up with. Okay, 0, 0, minus x, x and x. We don't really care about water because you don't include water in the equilibrium equation, equilibrium constant. So F minus would be at equilibrium 0.040 minus x, x and x. How do you feel about this? Not bad, right? Yeah. These are the stuff that we had before. Okay. Now, this is a base. I need you to realize that hey, I have OH, this is a base. Now, if this is a base, what do I need? I need KB. This is a base. What that means is I need KB. Is KB given to you? KB is not given to you. Ka is given to you. But that's okay. I can figure it out because Ka times KB equals KW. Okay, so what KB is going to be is going to be KW, which is 1.00 times 10 to the minus 14 over Ka, which is 7.2 times 10 to the minus 4. Okay, if I divide this together, what I end up getting is 1.38 times 10 to the minus 11. And that is going to be my KB. We're good so far? Okay. So, remember, KB is going to be product over reactant. So, I'm going to have x squared over 0.040 minus x. And again, KB is a really, really small number in this case actually, right? KB is 1.38 times 10 to the minus 11. So whatever this x is going to be pretty small compared to that. So what can I do? Yeah, I love this, making the math simple. I can assume that x is 0. I can assume that x is 0. If I do that, okay, what did you guys get for x? I got 7.43 times 10 to the minus 7. Yeah, hopefully that's what you guys got too. Now, what does x represent? That is going to help me out. What the x represent here it represents OH minus concentration, right? And that's going to be helpful. So the X represents OH minus concentration. That's great because every time I have that, what I could figure out the POH, right? Okay, so again, every time you have hydroxide concentration, figure out what you could, which is POH. So what I'm going to do, I'm going to figure out the POH minus log of 7.43 times 10 to the minus 7. Okay, so far so good. Again, what did the X represent here? The X represented the hydroxide concentration. And that's very helpful because I need hydroxide concentration or I need H plus concentration, hydronium concentration to be able to figure out pH or POH. You need one of those things always to figure out the pH or the POH. Okay, so if I do this, what I end up getting for POH, I end up getting 6.13. That's going to be 6.13 is going to be my POH. Again, I don't want POH, I want pH. But again, that's easy to do. What I'm going to do, I'm going to do 14 minus 6.13 and I'm going to get 7.87 and that is going to be my pH. That is going to be my pH. Okay, what is this pH? Slightly basic, right? I got a slightly basic pH and that's what we expected, right? We expected a slightly basic pH and that's exactly what we got. Slightly basic pH. So far so good? Okay. Now what I'm hoping you get out of this review session today is to be able to recognize the different types of problem, right? You go, oh, strong acid, a strong base, easy. Oh, weak acid, weak base, equilibrium, easy. Oh, this is a conjugate, also easy. I can figure it out in hydrolysis. Yeah? Okay. Ready for our last problem. Here is our last problem, and I saved the best for last. So, when you read this, actually, I don't even want you to read this problem. I just want you to look at this problem without reading it. You are probably going to go, okay, hold on a second. In this problem, I have HBr that is added to ammonia. Okay? HBr added to ammonia. What type of problem is that? You have hydrobromic acid added to ammonia. So you're going to say, oh, that's an acid-base reaction. That's an acid-base reaction. Now you can read the problem. Yeah? So, okay. Now this is mixing things together. This is a mixing problem. I have acid added to base. So when that happens, what I have acid-base reaction. And if remember, we said every time that you have an acid-base reaction, that reaction is not equilibrium, right? Single arrow. That reaction is not equilibrium. Now, when you have an acid-base reaction, you have to care about moles. You have to use moles to figure out the limiting reagent, okay? So remember that again, you see an acid, you see a base added together, it's an acid-base reaction. Acid-base reaction are the fastest reaction, one of the fastest reaction in chemistry. So single arrow, not equilibrium, I have to use moles and limiting reagent, okay? Now what I'm going to do, I'm going to put down this acid-base reaction. So I'm going to have HBr plus ammonia. Okay, here's my acid-base reaction, HBr plus ammonia. Don't forget that acid is going to lose a hydrogen and then base is going to gain a hydrogen. Acid is going to lose a hydrogen, base is going to gain a hydrogen. If that's the case, it's going to be Br minus and ammonium. Br minus and ammonium. So far so good? Okay, again because acid is going to lose a hydrogen and base is going to gain a hydrogen. Now here is my acid-base reaction. Now it's not an equilibrium, so I cannot use an ice, but I can use an ICF. What was ICF? Initial, change, and final. Initial, change, and final. Okay, now we're gonna fill up this table. Okay, But you need to remember that for the acid-base reaction, because you have to figure out limiting reagent, what you need is moles. What you need is moles. And you need to remember that what you need is moles. Well, for HBr, I made it easy for you. Don't get used to it. I gave you the moles of HBr already. 0.20 moles of HBr. Okay. For ammonia, I don't give you the moles, but you can figure out the moles because what is molarity? Molarity is moles per liter. Molarity is moles per liter, and I have the molarity of ammonia. You agree? I have the molarity of ammonia. I have the volume of ammonia, so I can just figure out the moles. 0.20 is the molarity, and is 1.0 liter. Okay, so because I have all that, so what I end up getting is 0.20 would be the moles of ammonia. Moles of ammonia. So far so good. Okay, so now I have the moles of ammonia also. What I'm going to do, I'm going to come over here, is also 0.20 moles of ammonia. Perfect. So I put the initial moles of each one. Now at the beginning, of course, I have none of that. What is the change? What the change is going to be, these got to go away, and then the product is going to be 4. Now, what is the limiting reagent here? This is a tricky part usually. What is the limiting reagent here? Now, usually the limiting reagent is the guy that you have less of, right? So which one is the limiting reagent? I want you to look at this. I can't hear you, but if there's someone around you, tell them which one is the limiting reagent here. Both are the limiting reagent here, right? Because remember, for 1 HBr, you use 1 ammonia. 1 HBr, 1 ammonia. If I have 0.2 moles of HBr, 0.2 moles of HBr is going to react with 0.2 moles of ammonia. You have exactly the same amount of acid and base together. So every single HBr is going to react with every single ammonia. You guys follow that? Okay. Because I have 0.2, I have 0.2. So what my change is going to be is going to be minus 0.20 minus 0.20 plus 0.20 and plus 0.20. Now, what that means, I'm going to have no HBr and no ammonia because I have enough HBr and ammonia 1-to-1 ratio. They're all going to neutralize each other out. And what I end up with is 0.20 Br minus and 0.20 ammonium. So far so good? Okay. Now, here's what you need to figure out. After you do an acid-base reaction, look at what is left over. And that is really key. What is left over? What is left over here? What you have left over, there's no more base, no more acid, no more ammonia, no more HBr. You have 0.20 moles of Br minus, and you have 0.20 moles of ammonium. Follow me so far? Okay. Now, Br minus is neutral. Why is Br minus is neutral? Br minus is neutral because Br minus is a conjugate of HBr, and HBr is a strong acid, right? Is a strong acid. I want to put SA for strong acid. So HBr is a strong acid. Conjugate of a strong acid is neutral. Conjugate of a strong acid is neutral. When you have strong acid or base, the conjugate is neutral. So this is not going to do anything to the pH, right? It's just like a neutral salt floating around. Now, how about ammonium? Is ammonium neutral? Ammonium is a conjugate of ammonia. Ammonia is a weak base. If you have a weak base, the conjugate is acidic, right? Is the conjugate base is acidic. The conjugate of a weak base is acidic. So I have a conjugate acid. Okay, now I'm going to repeat this one more time. I know you know this, but I just for my own good. One more time. If you have a strong acid or base, their conjugate is going to be neutral. If you have a weak acid, the conjugate is going to be basic. If you have a weak base, its conjugate is going to be acidic. So ammonium is a conjugate of ammonia, weak base, so this would be a conjugate acid. So it's going to be acidic. So far so good? Okay, so what we have left that is going to matter for the pH basically is our ammonium. Ammonium is what's going to matter. Now what is ammonium again? So what we have left is a conjugate acid is left. Conjugate acid is left. Now if conjugate acid is left, then what am I going to do? I want to do a hydrolysis, right? When we have a conjugate, we're going to do hydrolysis. Okay, let's do it. So what I have left over is ammonium, which is a conjugate acid. I want to do a hydrolysis and write the equilibrium reaction. This is my acid now, which means water is my base. Because remember, I know I keep repeating this, conjugate acid is still going to act like an acid. So acid is going to lose a hydrogen, base is going to get a hydrogen. You're going to get ammonia and you're going to get OH minus. Okay, now I have an equilibrium reaction. Yes, ice is back because I have an equilibrium reaction. So far so good. Okay, how much of ammonia do I have? Remember, this was moles. Okay, this was moles. But what's the volume of the solution? Is 1 liter, so it's not going to, it's going to be the same, but I still want you to pay attention to that in case if I give you a problem that it wasn't 1 liter. So molarity is moles per liter, and now in this case, ammonia's mole is 0.20, but over 1.0 liter, so we 0.20 molarity. But I want you to pay attention that you have to put molarity in an equilibrium equation because ice has to be molarity because equilibrium constant in molarity of product over the molarity of reactant. So one more time, when you have acid base, you want moles. But when you have equilibrium, you want molarity, right? You want molarity. And write this down. Write it down in purple. So you want molarity for an equilibrium reaction. Why? Because equilibrium constant K is concentration of product over the concentration of reactant. Alright, now what's going to happen after that? So at this point we also have none of this, right? Minus X, X and X, and then water is not included in an equilibrium constant because water is liquid. So what am I going to need? Don't forget, I have OH here. Oh my goodness, not OH. Why didn't anyone correct me? Well, because you couldn't. So remember, acid is going to lose a hydrogen and base is going to get a hydrogen. You were probably very confused. I was testing you to make sure you're paying attention. Acid is going to lose a hydrogen, base is going to gain a hydrogen. So far so good? Okay. If I confuse you, that was intentional. So over here, I'm going to have to use an Ka because remember, ammonium is a conjugate acid. Ammonium is a conjugate acid. It's going to act like an acid. So I'm going to use an Ka. Alright, so Ka is going to be product over reactant, x squared over 0.20 minus x equals, what is my Ka? Well, I give you Kb and not Ka. Well, that sucks, but that's okay. You can figure out Ka based on the Kb, right? Okay, so let's do that. Because if you remember, Ka times Kb equals Kw. You want the Ka, that would be Kw, which is 1.00 times 10 to the minus 14 over the Kb, which is over here. This is my Kb, 1.8 times 10 to the minus 5. You guys follow me that? Okay. Again, why do I need Ka? Because what you have is ammonium, not ammonia. I have ammonium. Ammonium is an acid. You know that because what you end up with is a hydronium concentration in the solution. So when you have an acid, you have to use a Ka. Ka is not given to you, but Kb is given to you. And that's okay because I can use this relationship to figure out what is the Ka. This would be 5.55 times 10 to the minus 10. That's the Ka. So 5.55, write it a little bit nicer, times 10 to the minus 10. So far so good? Okay. That's a small number. Yeah, that's a small number. So whatever this x is going to be so small compared to 0.2. So I can assume this x is 0 because whatever this x is going to be so small compared to the 0.2. So I can assume that's 0, which makes my math a lot easier. Okay, what do you guys get for x? I get 1.053 times 10 to the minus 5. Double check 1, 2, 3, 4, 5. Yeah? Okay. So that is my x. That's great. Now what is x going to represent that is going to help me out? What x is going to represent that is going to help me out? X is going to be the hydronium concentration. And that's going to help me out because I need the hydronium concentration to figure out the pH, right? So I need that to figure out the pH. So now I can just go pH is minus log of 1.053 times 10 to the minus 5. pH is going to be 4.98. That's my pH. Again, double check yourself. Is this a basic or acidic pH? This is the acidic pH, and that's what I expected, to have an acidic pH. Yeah? Okay. Now to kind of summarize, I like the review session. Hopefully you did too. So it was kind of, I gave you different types of problems. You can have a strong acid or base. What do? You can have weak acid or base. What do? You can have a conjugate acidic or conjugate base. What do? And the last one, you can have a mix of things, acid-base problem. What do? And the hardest one probably is the acid-base reaction, not an equilibrium. You are going to use moles, right? You're going to set the reaction up, not using mole is ICF, initial change final. And then once you do this, then you have to figure out what is left over. And based on what is left over, then you go based on that. In this problem, Br minus neutral, not going to do anything. What was left over was a conjugate acid. I have a conjugate acid that is left over. I have to do hydrolysis. I have to do equilibrium. So I set up an equilibrium and then I go through the motion. Okay. Really nice job for hanging in there. I know this was a lot. So hopefully you guys are getting this down. I will talk to you next time.